we were discussing the particle in one-dimensional box. In fact, the box was infinitely deep, and so the case was actually of unsymmetric infinite square wave potential. In the first part of this lecture, we have obtained some important results. Actually, the unsymmetric infinite square wave potential is defined in this manner. This is V of x equal to infinity for x less or equal to 0, and it is 0 in the region between x equal to 0 and a, and it is again infinite when x is greater or equal to a, as you can see in this figure. Actually, this is the definition, or you can say this is the potential distribution in case of one-dimensional potential box. And setting the time-independent Schrodinger equation for this potential, we have actually obtained two important results. The first one was the eigenfunction psi n of x equal to a square root of 2 over a sin n pi x over a in the region between x equal to 0 and x equal to a. And in fact, in the region x less than 0, the wave function was 0, and also in the region x greater or equal to a, the wave function was 0. In fact, in this equation, this n has the values 1, 2, 3, and so on. And the another important result was energy eigenvalue. We have seen that the energy eigenvalues for this particle are actually discrete or quantized, and this is defined in this manner: En equal to n square pi square h bar square over 2ma square. So these are the results which we have obtained actually in the first part of the lecture on particle in one-dimensional potential box. Now, today we will discuss some of the important part of this problem. So what are the important parts of this problem? Remaining parts you can see here. First of all, we will see the degeneracy of the energy eigenvalue in this case. You know what is this degeneracy? In fact, if corresponding to an energy eigenvalue, there is only one eigenstate or only one eigenfunction, or you can say only one quantum state, or you can say only one wave function, then that energy eigenvalue is called non-degenerate. But if there is a situation when for a given energy eigenvalue there are two or more eigenstates, then such energy state is called degenerate. So if you consider that corresponding to an energy eigenvalue there are g different quantum states or eigenstates, then such energy eigenvalue is called g-fold degenerate. This is actually what the term degeneracy means. Now we will see in the present problem, is this degeneracy in energy eigenvalue exist or not. For this, let us see some of the energy eigenvalue and corresponding eigenfunctions. As I have mentioned earlier that in this case energy eigenvalues are given by this relation En equal to n square pi square h bar square over 2ma square, and for n equal to n, the eigenstate or the eigenfunction or the wave function psi n of x is equal to this much, as you can see here. So now let us consider the lowest value of n. So for n equal to 1, this is actually the lowest value of n. And what will be the energy eigenvalue and the eigenfunction corresponding to n equal to 1? You can see easily. You can see the energy eigenvalue will be E1, and that E1, as n is 1, that will be simply equal to pi square h bar square over 2ma square. This is actually called the ground state energy, as you have seen in the earlier lecture, or the 0-point energy. Now see what will be the eigenfunction corresponding to this n equal to 1. You can see this eigenfunction will be psi1 of x, and this psi1 of x, you can see it is a square root of 2 over a sine pi x over a. Again, if we consider the another value of n, say n equal to 2, what will be your result? The energy eigenvalue will be E2, and this will be actually equal to 4 times of pi square h bar square over 2ma square, or you may write it 4e1. And the corresponding eigenfunction will be psi2 of x, and this psi2 of x, you can see from this general result, this will be a square root of 2 over a sine 2 pi x over a. So what we see here, you can recognize that corresponding to this energy eigenvalue E1, there is one and only one eigenstate, that is psi1 of x. Similarly, for the energy eigenvalue E2, you can see there is one and only one eigenfunction or eigenstate psi2 of x. So according to the definition, you can say that these energy eigenvalues are actually non-degenerate, not degenerate, because corresponding to one energy eigenvalue there is one and only one eigenstate. So no degeneracy in the energy eigenvalue exists in case of the unsymmetric square wave potential. So you can say that energy associated with different eigenstates are different, not same, and so all the energy states or all the energy levels in this case are non-degenerate. So what is the conclusion? Our conclusion is that all energy eigenvalues are non-degenerate, not degenerate, non-degenerate. But when we will discuss actually the three-dimensional potential box, then you will see that there will be degenerate energy state in that case. So remember, any energy level or any energy eigenvalue in case of particle in one-dimensional box is non-degenerate. Now we will discuss another important point, and this is regarding the nodes in eigenfunction. So for this, let us see this figure. In fact, in these two figures, I have plotted the eigenfunction psi n of x in against of x, and in another figure, I have plotted the probability density, that is mod of psi n of x squared. This is actually probability density in against of x. On the basis of this eigenfunction, which is defined here, you can plot, and you will see that for n equal to 1, that is the ground state, for the ground state eigenfunction, the curve is like this, and you can see from this figure, actually the in case of ground state eigenfunction, the eigenfunction actually vanishes at the end points of the well, that is at x equal to 0, this psi1 of x is 0, and at x equal to a, it is again 0. But at the middle, that is at x equal to a by 2, you can see this is maximum. This eigenfunction is maximum. So what does it actually represents? When you say that the eigenfunction is maximum at x equal to a by 2, and in second figure you can also see that the probability density is also maximum at x equal to a by 2. So actually this means the particle has maximum probability of being found at the middle. On the other hand, the wave function vanishes at the endpoints at x equal to 0 and x equal to a. So in fact, at these 2 points the probability of finding a particle is almost 0. But when we see the first excited state eigenfunction, that is psi 2 of x, see this figure, you can see again at x equal to 0 and x equal to a, this eigenfunction vanishes, but it also vanishes, it is also 0 at x equal to a by 2. So in fact, in first excited state, the probability of finding of this particle at the middle of the well is in fact 0. And similarly, you can see the nature of the graph for the second for the second excited state, that is for psi 3 of x in this figure. So the slope of the curve psi of x, that is d psi by dx, is discontinuous at the point x equal to 0 and x equal to a. In fact, why this is discontinuous at the point x equal to 0 and x equal to a? In fact, this is because the potential jumps from infinite amount at these points to the 0 value. And this is the reason that the curves are in fact discontinuous at point x equal to 0 and x equal to a. So you can see that the energy increases in proportion to n square, you have seen, as we go to the excited state. So one of the important feature of this curve or the eigenfunction is actually the nodes in eigenfunction. So what is this node? In fact, a point where the eigenfunction is 0 or the probability of finding of the particle is 0, such a point is called nodal point or node of the eigenfunction. You can see that in the ground state, x equal to 0 and x equal to a is node. In fact, in all states, either ground state or all excited state, these 2 points, x equal to 0 and x equal to a, are nodal points. But except these 2 nodal points, in ground state there is no other nodes. But in first excited state, you can see that x equal to a by 2 eigenfunction is 0. So x equal to a by 2 is a nodal point in case of the first excited state. But in second excited state, you can see the eigenfunction is 0 at 2 points between x equal to 0 and x equal to a. So there are 2 nodes between x equal to 0 and x equal to a in the second excited state. So you can see, as I have told you, that the points x equal to 0 and x equal to l are always nodes for the all eigenfunctions psi n of x. But apart from this, in ground state there is no node between these 2 nodes, and in first excited state there is only 1 node, and in second excited state there are 2 nodes between these 2 points. So you can see that between x equal to 0 and x equal to a, in general you can say the number of nodes will be n minus 1. So this is a remarkable fact. You can see here that each function psi n of x has in fact n minus 1 nodes between x equal to 0 and x equal to a. So you can see for psi 1 of x, n is 1, and if n is 1 then n minus 1 will be 0. So there is no node between x equal to 0 and x equal to a in case of the ground state of the particle. But in first excited state, our wave function is psi 2 of x. It means n is equal to 2 here. And therefore, n minus 1 in this case will be 1. And you can see in the first excited state, there is one node at x equal to a by 2. And when you see the wave function psi 3 of x, then n is actually 3, and for this n minus 1 will be 2, and you can see this figure, there are two nodes at this point and at this point between x equal to 0 and x equal to a. So actually this node formation is actually a special feature of the bond state potential. In fact, as the value of n increases, or you can say that as the energy of the system increases, the number of nodes also increases. And as I have told you, this is a general phenomena in bond state potential. So this is all about the nodes in eigenfunction. Now we will discuss a very important property of this eigenfunction. This is in fact orthogonality of the eigenfunction in case of particle in one-dimensional box. So see here, orthogonality. In fact, in previous lectures in quantum mechanics, we have discussed the orthogonality property of eigenfunctions or eigenvectors. And you know that the two different eigenfunctions are called orthogonal. In fact, when their scalar product vanishes. So if you consider that there are two eigenfunctions, psi n of x and psi m of x, and you will find the scalar product of those two, and if that scalar product will be 0, then you say that the eigenfunctions are orthogonal. So the eigenfunctions psi n of x and psi m of x are orthogonal if the scalar product of psi n and psi m, which is actually defined in this manner, integral from minus infinity to plus infinity. This is in fact all space. Psi n star of x psi m of x dx equal to 0. This is equal to 0. And in this case, you will see what will be the value of this integral. In present case, this product psi n and psi m, what will be this? Here all space means the space lying between x equal to 0 and x equal to a. So we will use the limits 0 and a here. And psi n star, that will be actually equal to root over 2 over a, because the function is real, so its complex conjugate will be also same. So this is root over 2a sine n pi x over a times root over 2 over a sine m pi x over a dx. And actually we will write it. This is 2 over a and integral 0 to a and this is integral sine n pi x over a times sine m pi x over a dx. Now we know that this integral is what? In fact, this integral is written as, this integral is written as, this integral is written in this manner. This is in fact a over 2 delta nm. You know what is this delta nm? This delta nm is known as Kronecker delta. This is Kronecker delta. And you know this Kronecker delta nm is equal to 1 if n is equal to m, and this is equal to 0 if n is not equal to m. So you can see this scalar product will be simply equal to delta nm. This is equal to delta nm. And so this will be equal to 1 when n is equal to m, and this is equal to 0 if n is not equal to m. So you can see if the eigenfunctions are different, then different means corresponding to different energy eigenvalue, then the scalar product of psi n of x and psi m of x will vanish, and so they are orthogonal. Therefore, we can say that the scalar product of psi n and psi m is equal to 0 when n is not equal to m. N is not equal to m. And this implies that psi n of x and psi m of x are orthogonal. Again, you have seen that this product psi n and psi m, this equal to 1. But when it is 1, you have seen this is 1 when n is equal to m. So this condition actually implies that these eigenfunction, this psi n of x is normalized. This is normalized. So combining these two results, you can say that the scalar product of psi n and psi m will be equal to Kronecker delta nm, and if it is equal to Kronecker delta nm, then you know that the eigenfunctions are orthogonal, and simultaneously they are normalized. So this is the condition for orthonormality. So these eigenfunctions actually form the orthonormal set of eigenfunctions. So this is the condition for orthonormality. Orthonormality. And you can say that the eigenfunctions in case of particle in one-dimensional infinite square well potential, the eigenfunctions are orthonormal. Now we will discuss the last important point, which we have in fact tell something regarding this earlier, and this is regarding the 0-point energy or the lowest energy of the particle in this case. What is this 0-point energy? As I have told you in the first lecture that the minimum energy of the particle according to classical point of view should be 0, but the quantum mechanical result does not agree with it. You have seen that the least energy of the particle in this case is not 0, but it is non-zero. So let us explain why the minimum energy of the particle cannot be 0 in this case. Actually, in case of the square well potential, no eigenstate with 0 energy exists. In fact, if the energy of a particle in this square well potential is 0, then the particle will be at rest with 0 momentum, because our particle is free. So here energy means kinetic energy, and if kinetic energy will be 0, the particle will be at rest, and if the particle is at rest, its momentum will be also 0. And this 0 momentum will be actually the violation of Heisenberg uncertainty principle. But how you can see it very easily? That you can say that if the energy of the particle is 0, then particle will be at rest. Particle will be at rest. So its momentum will be 0. Its momentum will be 0. So its momentum will be 0. So as I have told you, there will be a violation of Heisenberg uncertainty principle. How you can say that there will be a violation of Heisenberg uncertainty principle? Let us see what we will get according to Heisenberg uncertainty principle in this case. As you have seen that the width of this potential well is equal to A, because it lies between x equal to 0 and x equal to A. So you can say that the uncertainty in measuring the position of the particle inside the well will be of the order of A. So uncertainty in position of the particle, if we denote it by delta x, this will be of the order of A. And if the uncertainty is of the order of A, then what will be the uncertainty in measuring the linear momentum of the particle we can find from Heisenberg uncertainty principle. So according to Heisenberg's uncertainty principle, if delta P is the uncertainty in measuring position, then this product delta X times delta P will be of the order of h bar, according to Heisenberg uncertainty principle. And so this delta X, as you have seen, is the order of A. So this is A times delta P, and this will be of the order of h bar. And this implies that uncertainty in measuring momentum will be of the order of, this is just order, of the order of h bar over A. H bar over A. Now, as the minimum energy of the particle will be its kinetic energy, because potential energy in this case is 0, so the total energy is equal to kinetic energy. So E will be equal to T. T is in fact kinetic energy, and this will be actually equal to delta P square over 2m. Delta P square over 2m. And this will be, let us substitute the value of this delta P from here. This will be h bar square over 2ma square. H bar square over 2ma square. So you can see the energy of the particle cannot be 0. This is not equal to 0. So in accordance with Heisenberg uncertainty principle, the minimum energy of the particle inside this box cannot be 0. Its least value will be actually equal to of this order. So the minimum energy will be never 0, and hence the 0 point energy of particle in case of particle in one dimensional box is not 0, but it is equal to pi square h bar square over 2ma square. So these were some important facts regarding the particle in one dimensional box. Now, till now we have considered only the situation or the state of the system which is actually independent of time. Now let us consider the time evolution in this case, because till now, as I have told you, we have dealt the situation of a stationary state, but for the most general solution of time dependent Schrodinger equation, we can consider the time evolution, and we will write the wave function when the wave function will be actually time dependent. So we can say the most general solution, of the time dependent Schrodinger equation. Time dependent Schrodinger equation are given by, in fact, in mathematical foundation of quantum mechanics, we have already discussed how time evolution is considered in an eigenfunction. So using those ideas of previous lecture, you can write that psi of xt will be equal to what? This can be written as summation n 1 to infinity Cn, in fact Cn is a constant factor, psi n of x. Our time evolution factor is written by e raised to the power minus I en times t over h bar. And as you have seen in the present case, what is this psi n of x? This is a square root of 2 over a sine n pi x over a. So, and that 2 over a is independent of this summation, so we will write this 2 over a outside of the sign of summation. So this is a square root of 2 over a summation n 1 to infinity Cn sine n pi x over a. And you see here this En is the energy of the particle in nth state, that is when n is equal to n, and you have seen this En is actually equal to what? This is in fact n square times E1. This is ground state energy E1, T and over h bar. So this is actually the general solution of the time dependent Schrodinger equation for this problem, because we have considered only the stationary states to solve this problem. But if you will consider the time evolution, then the eigenfunction or the wave function for this system will be like this. So this was all about the particle in one-dimensional box. And after this theoretical aspect, in the forthcoming lecture we will see some of the important problems related to this particle in one-dimensional box. In fact, the problem based on the particle in one-dimensional box is very important for the civil services, for the NET JRF examination. You will find that several times direct questions are asked from this concept.